Our objective is still the same as yesterday. It is solve a linear system using a graph or a table. Now, sometimes, like, think about the homework that you had last night. You probably could have found the solutions to that without a graphing calculator, because you guys know how to graph. And when we do get to the test, you are going to have to graph the lines yourself. And we really have already tested on that before, especially when it's when y equals mx plus b formula. So what we're doing today, and what we did a lot yesterday, was find out how about if we want to use our graphing calculator just to make sure, make sure all of our math is good. And today is going to be, well, it's very step intensive. So I'm going to tell you what we're going to do. And then, like I said, ask you to stop me if I get going too fast on anything, because you'll know this is a long process and it's going to take us a while. Here's what we're going to do. We're going to take one set of data here, either New York or Los Angeles, and we are going to do linear regression on just New York and the dates. And we're going to have the calculator kick out a line of best fit for that. But we're not going to write it down. We're going to tell the calculator to store it for us so that we don't have to write a bunch of nasty decimals. Then we're going to set that equation aside, and we're going to write another linear regression model for the years and Los Angeles. So we're going to get the calculator to get that line of best fit, and we're going to store it in the calculator so we don't have to write it down. Then we're going to do what we did yesterday. We're going to put both of those on the same graph, and we're going to find out where they intersect. So this is a long process. 2-5 was where we did line of best fit. But now we're going to add on to that what we did yesterday, which was where do they hit each other? Where is that intersection? So it's going to take a while to get this stuff in the calculator. So this says we've got a population. The table shows the population of New York City and Los Angeles metropolitan regions from the census reports from 1950 through 2000. Assuming these linear trends continue, when will the population of these regions be equal? What will that population be? That's why we have to see those lines, because they want to know when do they match? When are they equal to each other? And we can only see that if we can get this graph. So first things first, we're not going to put in 1950, 1960, 1970, etc. We're going to use a 0 year. So we're going to call 1950 0. And then 10 years later, of course, is 1960, 20 years later, 1970, 30 years later, 1980, 40 years later, 1990, and 2000 will be 50. So we're using a 0 year of 1950. That's the first thing that's going to save us a little bit of time. The second, and I'm not sure I like this, but the book says round these numbers to the nearest millions. We're going to do millions in one decimal place. Because really you lose something. You know, you look at all those numbers that are up there and you say, well, I'm just going to round that. You lose some information. But that's what they want us to do, so that's what we'll do. For instance, we're going to round this to 12.9 million. This will be 14.8 million, 16.2 million, 16.1 million, 18.1 million, and this one will round to 21.2 million. So that'll be the first set of data that we put in. We'll put the years in and we'll put the New York City stuff in. Well, then we're going to have to come back and put the LA stuff in. So we might as well do that rounding right now too. That one would round to 4.4 million, 6.7 million, 7.0 million, 11.5 million, 14.5 million, and 16.4 million. I want to make sure everybody gets that down because I have to take this off the screen so I can show you the graphing calculator. So make sure you have those numbers that we're going to use on that. All right. Anybody need more time to get those rounded numbers out? Calculator time it is, and it's much faster for me to use the mouse at my desk than it is sitting here trying to punch these in. So, first things first. We may have some old lists in our calculator that are in the way, and we don't want those. So the easiest way to get rid of all of them at once is to hit second and then the plus key. And notice number 4 is clear all the lists. Now when we hit enter, that's going to take every piece of data that we have in there out. And it tells us it's done. So now, how do we get the stuff in there again? You guys should know this. How do we get the information in? What do we do? Stat, edit. Oh, look at that. Nice, clean, fresh lists. So list 1 is going to be our years. That's the 0, 10, 20, 30, 40, and 50. And then list 2 is the numbers for New York City. So 12.9, 14.8, 16.2, 16.1, 18.1, and 21.2. And then arrow over one more time because we need Los Angeles. 4.4, 6.7, 7.0, but you don't need the 0, the calculator ignores it anyway. 11.5, 14.5, and 16.4. All right, now don't get ahead of me here because I know that you know how to do linear regression. You did a really good job at that. 1 second, Jake. But there's one step here that I'm going to give you that's brand new. All right, so I need you to watch for everything I'm going to do. And everybody's calculators are a little bit different, which means I have to show different people how to do what. Oh, it didn't grab the 1 again. That 1 is sticking or something. Thank you. That happened in 3rd hour too. Stinky little 1. Yep, it still didn't take it. There we go. I guess I went too fast for it. All right, so we're going to have this make a line of best fit for list 1 and list 2. We're going to have the calculator store it. Then we're going to come back and make another line of best fit for list 1 and list 3. So we have Los Angeles done. And then we're going to let the calculator tell us where they intersect. So first things first, stats, calculate, so we have to arrow to the right once, linear regression, and here's where we're going to have 2 different sets of calculators in the room. So some people have this nice vertical list that I have right up here, and those are the newer calculators. Of course, my older yellow ones that I handed out aren't doing that. You're seeing this. L-I-N-R-E-G and nothing else. So here's what we have to do with the old yellow ones. You're going to hit number 1 to tell it list 1. And then you're going to hit the comma button, which is right here above the 7. And then you're going to hit number 2 to tell it list 2. And you're going to put another comma there and you're going to stop. This slot right here is where we're going to catch up with. So those that have the old yellow calculators, you can go ahead and put that in there and then just wait for us to catch up. So now, this one has list 1 in as the X list. That's exactly what I want, so I'm just going to hit enter. But it has list 3. That's not what I want. So I need to hit number 2, so that I can get that data from New York City in there. Now this frequency list, we don't care about that one, but here's what we want it to do. We want the calculator to store this for us so we don't have to write it down. So I think, well, how can I get it to store it? Well, I want to see it graphed. And whenever we want to graph something, we have to graph y equals. So what I need is I need a variable right there that says y sub 1. Well, there's a button on our calculator that says VARS, just to the left of the clear key. That's where we go when we need variables. So this is where everybody joins us back in. So the old calculators have linreg, L1, L2 with the commas, and now everybody's going to hit variables. And look at this right up here. Y variables. Arrow to the right once. we've been graphing functions, so we're going to pick number 1. And look at that lovely little list of all the things that we have to graph with. So I'm just going to hit number 1, y sub 1. And now we can go down and hit calculate. With the old calculators, if you just hit enter, it'll do that regression. And hit enter. So there's our line of best fit for the New York data. Y equals 0.1465 blah blah blah, x plus 12.88571429. Now, I don't know about you, but I don't like having to write down all of those decimals, and we won't have to. But while I'm here, I'm looking at R. Is this a pretty good line of best fit? That's not too bad. 0.96, that's a pretty good line of best fit. And like I said, my hope is that I don't have to write this down. And where I wanted the calculator to store this was y sub 1. So let's hit y equals. Look at that. Nasty decimals and all. And we didn't have to do anything except put y sub 1 in that slot. That was the only thing we had to do. So we're going to leave that there. That's New York. Now we need to do Los Angeles. So everybody's back to stats. Arrow to the right once for calculate. Number 4, linear regression. List 1 is okay, but now we have to change list 2 to list 3. So the old yellow calculators, you need to do lin reg L1, comma L3, and hold on because we're going to go to the variable piece again. So second number 3 gives me list 3. Down past frequency list to store. Now, I'm not going to store it in y sub 1. I already have the other line there, but I want y sub 2. Can you talk me through where to get it? Do you remember the keys? Vars. Y variables. Number 1. And let's just pick 2. So now everybody on the old calculators, you're going after y sub 2 as well. So variables. Arrow to the right once for y variables, number 1 for functions, and then pick number 2. We don't want to write over the top of the other one that we just did. Down to calculate and enter. Is this a good line of best fit? Even better than the other one, right? So what? You're just not getting the other value. Somebody turned the diagnostics on. It's okay. You can see them up here. All right, so this is an even better line of best fit for Los Angeles, right? Anybody else having issues with the calculator? Okay, so what we need to do now is see these intersect. That's what we want to see. But you know what? It's not going to work in a negative 10 to 10 window. So if we hit zoom 6, we're going to see a whole lot of nothing. Don't hit zoom 6 on yours. I just want to show you. Our numbers were nothing like that. So, oh, well, we can see one of them. We can't see the other one. So let's go under window. And what were our list 1 numbers? Looking back at the table, what did we put in for list 1? 0 to 50. Okay, so let's try maybe -5 to, I don't know, maybe 100 for years. So -5, 100. Oh, I'll just use the keypad here. Y values. What was the smallest number that we put in for millions? 4.4? Well, then maybe start with 0. That wouldn't be awful. And we went up to 21.2. Is that the highest, everybody? Okay, so 30 sounds good. Let's go with 30. And then we hit graph, not zoom 6, because we don't want the negative 10 to 10 window. So let's hit graph, and let's hope we can see both the blue and the red, and then we can see where they hit each other. Oh, right there. There it is. Now, it's time for Blinky. Do you remember how to call Blinky out? How do we call Blinky out? Oh, something goofy, Jake. Second calc, yep, second trace. So that'll get you the calculate. Intersection. What's happening is your calculator is calculating. So let's do second. And then do number set. We'll just reset all that. All right, did you get Blinky already? No? Is there an issue? Something else wrong? Second trace, number 5, and hit enter 3 times. Okay, yours is doing the same thing. Yeah, something. Oh, you accidentally did the same direction twice. I think it's on the next page. Next page. So now if you hit graph, your window should be ready. Yep. Alrighty. I'll just do it up here. Second trace, number 5, and then the blinkster shows up. Enter, enter, enter. 86.8 and 25.6. That's our answer. 86.8, 25.6. But we have to interpret that. I mean, it's like, what's that mean? Because it said, assuming these linear trends continue, when will those populations be equal? Well, about 87 years later than 1950, because we use that as a 0 year. So 1950 plus 87. Sometime during 2037, they will both be 25.6 million. That's when they would be the same. So they were both rising, one faster than the other one. They're eventually going to hit each other. So now we're going to do this one more time so you guys can help me out a little bit more with this. Now what's wrong? right, so let's do it one more time. Let's go one more time. This time the data is for San Diego and Detroit. So again, we're not going to use 50, 60, 70, 80, 90, 2000. We're going to use the 0 year. So that means we don't have to do anything with list 1. List 1 is perfectly fine. But I'm going to clear out these two graphs that I just did and get back into stats, edit, and I have to replace list 2 and list 3 with the new numbers from San Diego and Detroit. So I'm going to arrow back to list 2, up, clear, enter, list 3, up, clear, and enter. And now for list 2, I need to put in San Diego, but this is kind of weird because San Diego started off with 334.387, so rounding to millions, that would be 0.3. And then 0.6 for 573,224. 0.7 for the next one. 0.9. 1.1, finally looking a little normal again. And 1.2 for the millions for San Diego. So San Diego, is the population increasing or decreasing? Increasing. You know, right now, we just did a problem with Los Angeles. That linear trend that we saw with Los Angeles isn't going to work because Los Angeles, a lot of it has been on fire recently. And so there may be some people that decide not to rebuild there anymore. But this data, San Diego, still might be pretty good. Now Detroit. Detroit is 1.8. 1.7. 1.5. What's happening to the population of Detroit? It is getting smaller, and that's because when they had to bail out all of the car manufacturers, they didn't have the jobs anymore, so people left Detroit. And that last one will round to 1. So, I guess I'd be thinking at this point, well, these numbers, maybe we can just use the same window when we graph later, but what we have to do is we still have to get those lines of best fit. So remind me, take me through the steps. How do we get the lines of best fit? Stat, calculate, number 4. What do I want to do first? List 1 and list 2. I'll do those first. And how do we get the y? Vars, y variables, number 1, number 1. Yeah, we'll just override that first one. And in. So there's the first one. Is that enough? Need the other one. Yep, we can go check and make sure that's in there. It's beautiful. It's in there. But we still need the other regression. So what do? Stats again. Calculate. What do I have to change? List 3, exactly. List 1 is good, but list 3. So second, number 3. And then what do we want to put in for the y's? Y sub 2, yeah. So variables, y variables, number 1, number 2, enter, and calculate. And if we go to y equals, they're both there. They're both there. And look at this one has a negative slope. That matches what we said. Detroit's population was going down. Well, I hope the window that we had for the other one will still work. So I'm just going to hit graph. I'm not going to try and change any of that. But uh-oh, these populations were much lower, weren't they? We've got a lot of dead space up here that we don't need. We have too many y's. So let's go into window. And let's not go to 30. Let's maybe go to 10 for the y's. And try it again. Blinky could have found the answer for us on the other window, but this is a little easier to find. What's up, Calissa? Okay, explain to me what your step was. Find the intersection. Everybody that's right there, find the intersection. Alrighty, did Blinky give you your answer? Second. Trace. Number 5. Enter, enter, enter. And there it is. Callista, because of time, I'm just going to have you follow along with what we're going to do here, okay? Otherwise, we won't have time for the non-calculator stuff we're doing. Alrighty. So, what we found out here was our intersection was, oh gosh, didn't even look at it. 40.7. And was the other one 1.1? So, 1950 was our 0 year. We round that to 41 years. And if we had time, I'd like to look this up and see if it was true, because 1991 is already passed. So, in 1991, they were equal at 1.1 million. Now, we like that. There's an answer. There's one answer. We like to get an answer. And so the other part of what we have to do today, besides being able to get the calculator to find that intersection of those two lines, is talk about what do we do when things don't work out. I mean, in yesterday's assignment, you guys graphed one set, and they ended up being parallel lines. And that brings us to something we really dislike doing in math, and that is telling somebody that there's no solution. We like to have an answer. Even if we tell them, hey, it's all real numbers, that's a nice thing and we like it. We don't like it when we can't tell people that there's a solution to something. So there are some fancy names that we're going to go over. And notice, if you didn't already flip to the next page, this has that sequence of calculator buttons that we were using so that you didn't have to write every little thing down as we went through it. You can use this as you're working through your assignment.
You don't have to.
No, it's not in there?
Before.
Oh, it's on the page before. Okay, so it's in there.
Yeah.
You can refresh back to that. Okay. So when we get answers, that's what we like. There's these words consistent and inconsistent. Consistent means when we're doing things, well, like normal. You know, when you're doing the same thing all the time, that's consistent. Inconsistent is something out of place. Consistent, we love to tell people the answer. So if it has an answer, that's a consistent solution. But if we have to say there aren't any solutions, there's no solutions, that's called inconsistent. Now, if it is an answer, it could be that you have just one answer, and that's called independent, just one. But it could be that you have to say all real numbers, and that's dependent. And let me show you why with these graphs. So with the graphs, graphical solutions of linear systems, we love this. We see two intersecting lines, we say, bam, right there, that's where your answer is, and we give the answer. So that's consistent with what we like in math, getting one answer. And it's independent, because there's only one. When you're independent, it's you, all by yourself. And then in the middle, why is there only one line? There's not one line. It's the same line, and blue and red make purple, everybody. That's why that's purple. It was red, and then they graphed a blue one right over the top of that. Those two lines are hitting each other all the time. So we do get a solution, so it's consistent, but it's dependent, because there's not just one. There's infinitely many solutions for that. And then finally, this is the one we don't like. If the lines are parallel, we have to say, hey, there's no solution. And that's inconsistent. We don't like it when we have to tell people there's no answer here. There's no solution. So if you can get an answer, it is consistent. If you can't, because they're parallel, it's inconsistent. If you get one answer, it's independent. And if you get infinitely many, then it's called dependent. So this is just some vocab. And what we want to get used to is not necessarily having to graph them. We want to look at the lines themselves in equation form, and we want to see, can we figure out which one this is? So I'm going to start with the 4y minus 2x equals 6. And I'm going to solve for y, because when we see y equals mx plus b, we know that that's a unique line. So we would add 2x, and we would divide by 4. And that would give us y equals Then the bottom line is much easier to get y all by itself. And all we're going to do is divide everything by 8 and do a little simplifying. So y equals 1/2 x minus, well, 4 goes into 12 3 times, and into 8 twice. So here's what I'm looking for. Are they exactly the same line? No. One's a plus 3 halves and one's a minus 3 halves. Do they have the same slope? Oh boy, they're parallel. That's inconsistent. We can't give these people an answer. Inconsistent, because we would have to say that this has no solutions. We don't like that in math. We want to be able to tell people what the answers are. And that's what we spend most of our days doing in math, is telling people what the answers are. So that's inconsistent. So now we're going to look at different examples down here, because obviously that one isn't going to meet all of the different types of names that we had. So the top one here, negative 3x plus y equals 4, what would you do to get y all by itself? Yeah, just add 3x. Both sides. So that one didn't take too long. I'm going to change colors for x minus 1/3 y equals 1, because this one's got kind of a goofy step we don't have to do a lot. What would your first step be, no matter what? Subtract an x from both sides. So negative 1/3 y equals negative x plus 1. Now here's the goofy step. Normally we'd say, hey, let's divide everything by negative 1/3. We don't divide by fractions. We multiply by the reciprocal. So we're going to have to multiply everything here by negative 3. Every single term gets that negative 3. So this will be y equals 3x minus 3. Now what I have to do is take a look at my red equation and take a look at my blue equation and check. Are they the same line? Should we be writing consistent and dependent because there's an answer and it's all real numbers? Nope. Are they parallel? Yes. There's no answer again. No solution, which is inconsistent. So no solution and inconsistent. They put 2 of those in a row. Got it? Well, let's hope for something different from B. 2x plus 3y equals 1. How are you getting y by itself? Okay, put that phone down. Subtract 2x from both sides. Then what? Divide by 3. Hopefully the other one won't be so much work. It isn't, is it? So how do we get y by itself for the red one? That's it. All right, red one, black one. Are they the same line? Not a chance. Are they parallel? No way. Well, that's what we want, because that means these 2 lines are going to intersect at one point. So this is consistent and independent. Consistent because we had an answer. Independent because there's only one answer. All right, one more to go. Okay, we don't have to do any work for the top one. I like that. What do we do with that? Subtract 6x. Divide by negative 3. Blue one. Green box. What do you notice? They're the same line. That means this has infinitely many solutions, but it is consistent because we get to give them a solution. So consistent, infinitely many solutions. these, yeah, all we have to do is basically get them solved for y, to just tell them consistent, inconsistent, independent, dependent. The rest of it is, yeah, we're going to use those graphing calculators. So I know I'm running short of time, but I need to lop a couple of these off. So we're going to go to 43, and then we're just going to stop. Right there. All right. Now the graphing calculator thing, I know for some of you you're saying, oh, this didn't go real well, but it really did. Usually, I'm going all over the